All right, great. Hi, folks. I'm Colin Faber. I'm with Whamcloud. I've been part of the Lustre community for many years. Some of you guys know me. Some of you don't. But originally, I started with CFS and kind of floated from company to company over the years. Today I'm here to talk to you about a feature that we've been developing since October of 2022, kind of quietly in the background, to improve Lustre in its overall functionality. The primary developer of this feature is Artem Blagodarenko, very capable engineer and amazing person. So let's get started. So why did we decide to develop this feature? First and foremost, is we saw it as a potentially cheap and easy way to reduce the cost per gigabyte of stored data. If you can reduce that, especially on things like expensive flash systems, then you can effectively provide more storage to your end users. Secondarily, we get an inexpensive way of improving the overall network performance for our I/O. This helps greatly in the sense that ripping out and replacing existing network systems can be very expensive. And of course, thirdly, I know that there are other compression proposals out there and solutions. However, all of those seem to leverage the server and the various backends. In this case, we wanted to ensure that we were leveraging the client itself. And this is, of course, because clients are infinitely more scalable than the servers. So the Lustre client-side data compression feature itself provides a transparent mechanism that is configurable per file or directory via standard Lustre tools. It is completely transparent to end users, of course, when configured by an administrator, and the compression speed is scalable based on the number of client CPU cores that you have available. So what's the difference about this compression model compared to other stuff that's been out there in the past? Of course, again, it's a client-based compression model. Compressed data is stored on the servers, and compressed and decompressed on the clients. So there's no additional CPU overhead that takes place on the servers. This works with the LDISKFS file system instead of having to be kind of forced into using a ZFS-backed file system. Not that there's anything wrong with that, but again, we're trying to keep it as standard as possible across the board. Right now, we provide 4 different compression algorithm support. However, this could potentially be extended in the future, depending on what comes out and what's desirable. LZO is provided, generally in just about every modern kernel. LZ4 is provided in even more modern kernels by default, and gzip is coming down the pipe at some point. So, but in this particular case, we have specific modules and stuff that will provide this that leverage the crypto framework. The framework itself is reasonably easy to extend. We can support up to 255 different possible compression types at this point. Which, I think is plenty, but who knows? More famous people than me have made different comments that sound very similar. And of course, like I said, this does not depend on ZFS compression on the server. So some of the features that we have is right now we fully support in-kernel LZO algorithms. We have backported more modern kernel LZ4 algorithms and variants for older kernels. This allows us to kind of bolt in the LZ4 support into the older kernels, which may not have that support yet, which is kind of nice because it's a reasonably good compression algorithm. Per file component, enable disable compression algorithm and level for each chunk that you're storing there. This is useful because you can kind of tailor your compression needs on a per chunk basis. This can be set for a directory tree or a full file system. It can be turned on and off. There's no need to configure the file system ahead of time to support this. Existing files can, of course, be recompressed during the write process or during a migration process. Again, this is all transparent to the application itself. It's all dependent on the layout that you've selected which supports compression. Older clients will see the compressed files, however, they won't be able to access the data. as they have no compression support in those older clients. This should be fully compatible with all of the existing Lustre features, with the only notable one being encryption, and it will be compatible with that. However, there's a specific order of operations that will have to take place. We'll of course want to compress first and then encrypt. Otherwise, you're trying to compress a bunch of random data, which doesn't ever compress very well. And of course, we're not changing any of the on-disk structures, so everything remains the same. There's no need to reformat the file system to support this. We'll just kind of work out of the box once you've deployed it. So part of this is updating the tools. Some of the tools, the two major tools that we've had to update here is, of course, LFS get stripe and LFS set stripe. This allows you to set the compression type as well as the level and the chunk size that you find most optimal for your particular workload or file system. LFS get stripe, of course, is there and provides the new compression information to let you know exactly what the layout of the file looks like. In addition to that, we've extended LFS find to provide you with the ability to find either compressed or uncompressed files in a particular layout, if you're so inclined, or a particular compression level. So you can go through and say you've done a real quick basic compression across the board of your data set, and now you want to come back with some other process and a different set of clients later on, identify those, and then recompress them at a higher level. Okay, part of the compression pipeline is, as I said, this is all within the client itself. So we reserve a compression pool memory for this client to perform this work. We then construct a specific RPC, which has a compression header, the compressed data itself, and then some alignment padding at the end of that. Client reads and writes whole chunks, decompresses to and from the RPC staging buffer. And this can be done independently, single client, or in parallel across multiple clients, multiple cores to achieve maximum performance. So in this sense, this kind of provides us with the scaling ability that we're looking for with our clients, and allows us to leverage the potential excess CPU cycles that may be out there in your compute. Larger chunks, of course, can improve compression depending on the algorithm. This is because some of these algorithms use specific definitions databases that are constructed based on the data that's found within the chunk. So, you could potentially move to a larger chunk and get a higher compression ratio. However, there is a trade-off there where your read, modify, write overhead is going to be a little bit higher. So they're likely that based on the data you're writing and the job, there will be a sweet spot that you'll find for this. Optionally, you can write, uncompressed. You can write an optionally. You can write you can create a mirror that's uncompressed. You can then perform read and write, random I/O against that mirror, and that mirror will then, be migrated back into the compressed file, and the mirror itself could be destroyed at that point. So, and of course, we can do data recompression or compression or decompression during mirror and migrate operations, via the transfer agent. As part of this, we've had to look at the LDISKFS allocator, MBAlloc, and make some changes here. The current allocator will always want to provide holes basically in the chunks for the logical offsets. In this case, the OST will write the chunks starting at the file logical offset, for that the allocator itself understands, and from that point, the client must read and write whole chunks starting at the even number of the chunk offset. So it's great for writing and performance there. However, it's not great for packing data when we're looking for overall data density. From the LDISKFS perspective, compressed chunks have holes between them, of course, In a file block allocation, for example, the example we have here, 64 kilobyte chunk compressed to 24 kilobytes. The next chunk will have a 40 kilobyte hole in it, which is, again, suboptimal for our packing strategy. From an LDISKFS logical offset perspective. So again, what this means is we've successfully compressed the logical chunk that we've sent in. However, we've now effectively lost a good chunk of that space once we write it out to disk. So what we're doing is we're optimizing the on-disk blocks to be more contiguous, and at the same time we send a specific flag to the allocator via the RPC and notify the allocator that we're running with compressed data, because the allocator itself, it's just looking at the data as data. It doesn't recognize whether or not this is compressed or not. So it's trying to make the best decision that it can based on the workloads that we've run over the years, and those workloads are not a good informer of the compression system that we're implementing here. So again, this flag will inform the allocator to not leave those holes in place for the optimization that it would typically make, and to just pack those chunks a lot more densely. Here's an example of what I'm talking about here. The existing LDISKFS optimization is going to write those chunks out, but we're going to end up with those gaps, and this is going to decrease overall read performance. It's also going to decrease overall storage capacity, and it's not going to be great for our strategy of trying to get maximum storage capacity out of the existing disks that we have. Okay, so we did some testing, and we're still in the process of constructing this feature. Some of the stuff has been committed to master, but a lot of it is just not ready for master. It's still pretty rough. So what we did was we constructed a special kernel module that allowed us to go through and test these various compression algorithms through the kernel. We haven't been able to test all the way through the entire pipeline yet. We're working on that actually as we speak today. And so far we've tested 3 different data sets. One of them is synthetic binary data with repeating patterns, so it should compress reasonably well. The other is just text data of Lustre sources, and of course the last is HDF5 oceanographic data that we pulled from various sources. And as I said, comprehensive performance testing is still ongoing. We hope to announce further results probably within the next couple of weeks of where we're at, and then as we continue to develop the code, we'll continue to push it upstream. So looking at this with some of the compression algorithms, we can see that the LZ4 performs reasonably well at speed, but we don't necessarily get the highest compression ratio. Whereas the known trade-off, of course, is the higher the compression ratio, the slower it's going to run. So we, as I said, we've gone through the various data sets. You can see that here, of course, and here. And I think the HDF5 climate data is probably most representative of kinds of realistic data that you would see. And of course, as I said, performance and compression, performance and compression algorithms and considerations. The things that we have to look at here is the overall performance and compression ratio, depending on the data being compressed, the ability to define the algorithm, the level, the chunk size, all of that stuff affects the compression speed and compression ratio. Compression algorithms and chunk size settings, vary differently and have different demands on CPUs. So you could potentially dial this up or dial it back down, depending on how much available CPU you might have in your compute environment. The compression buffer pools need to allocate memory, so there will be additional memory constraints on the clients as a result of this. And of course, block allocation on targets will behave differently for compressed data because we're kind of removing some of those past optimizations that were added in this case. Based on all of that, though, of course, flash-based disks will yield the best overall performance for this, and generally that's the overall target for a feature like this, where you can create those chunk sizes in the erase block size for those flash disks, reduces wear on the disks, as well as providing potential optimum read-write characteristics for them. So part of our testing, of course, is producing unit tests, and one of those unit tests that we produced here is a basic compression test using the compression pipeline. As you can see here, we were able to successfully compress through this pipeline. We can demonstrate that when you look at the file size that's reported is, of course, going to be the original file size. However, when you look at the block count is significantly reduced as a result of the compression action that's taken place. And of course, when we examine the checksum of the file, well, the checksum of the file from original through to compressed through to decompressed is identical. So what about ZFS as a backend? Because we talked about LDISKFS here. Can we use ZFS as a backend? Yeah, possibly, yes. We haven't started testing this yet, but we may at some point in the future as we progress the development of this product, or I should say this feature, to store data directly to ZFS objects. Of course, we need to do a lot of testing here to ensure that this works correctly, just against LDISKFS, but ZFS as well. And the client may need to use slightly different compression headers and types to fully integrate with the ZFS OBD. Client-side data compression is focused on LDISKFS primarily, but however, there's nothing that prohibits us from using ZFS as a backend. If we find that ZFS needs specific hints to work better, things like, if you already have compression on a pool and stuff, we potentially would send the OBD BRW compressed flag to it and inform it that, it may not be able to do full compression on the data that we're sending in because we've already compressed it. And of course, ZFS already is a copy on write approach, so it assumes new block allocation on every write. So the holes in the allocation, file allocation, are a lot less problematic, which differs from LDISKFS. As it's a different architecture for the backend file system. So when are we expecting to deliver this feature? Right now, the client-side data compression feature is expected to be available in the 2.17 release of Lustre. It will likely need both client and server updates to fully support this. However, as I said earlier, if you're running older clients and you run into compressed data, the older clients will see the different layout type. We'll be able to see the data, see the files themselves in the directories, but they won't actually be able to access that data until you've upgraded them to something that supports this. Major functionality continues to be under development right now. We have the basic client and server tools ready to go, and we're in the process of testing all of that. Further optimizations and cross-feature integration is ongoing, so we can ensure that everything functions as advertised. And client-side data compression specific testing for performance and stability, again, that's ongoing, and will likely continue right up until GA of 2.17. And as I said, we've been actively developing this feature since October 2022, and it's a major push for us to get this integrated because we think it will help with Lustre. So. That said, thank you guys, and is there any questions? At least I'll try to answer your questions.
Hi, my name is Ellis Wilson. I'm a Principal Engineering Manager at Microsoft. I had a question about the block allocator. So you said that you had optimized it for basically space savings, but it seems like it might, especially for spinners, like for files that are modified over time, they would end up being inherently unordered, so nonlinear, because you're going to move them to someplace else rather than having that space, since you've basically gotten rid of the sparseness between them. Yes. Okay. So that's is there any availability to turn that off?
Yeah, I mean, potentially we could provide the ability to disable that via tunable.
Okay. And then the corollary question was, is there any complexity with supporting sparse files from the client side if you turn this on?
No. As far as we know at this point, sparse files should be fully supported.
Okay. And then last question, Any HSM concerns? I don't think there should be because you basically just have a client on the front end for most of that work, but I wanted to say it out loud because I didn't see it in your list of supported features.
Yeah, there shouldn't be any HSM concerns. You know, if you're running that, you know, if you're running HSM, the client itself is going to be providing the compression and decompression. I guess the only caveat there is as you're pulling the data off of the file system itself and writing it to, you know, wherever it's going, you know, you're going to be decompressing that along the way. So what you see on the file system for overall capacity may not represent what you actually get in the HSM side of things. So, you know, you'd have to calculate based on blocks used versus the space reported.
Thank you. Appreciate it.
Yep, of course.
Yeah, one core, you know, additional comment about the holes in the files. The one thing that isn't going to work very well is seek hole and seek data, because it will be, you know, hard to know exactly what is data and what is like the hole from the compression, right? And so, you know, if it was integrated with ZFS compression or something, that it already understands the difference there. But other than that, I mean, you can still have file holes, right? There's no data written for the compressed part of the file, right?
But that's on the client side.
Yeah.
We would just get normal sparse semantics there, right?
No, but the thing is seek hole and seek data is passed through to the OST to know, well, because the client doesn't know what the blocks are allocated, right? So it has to ask the OST what blocks are allocated, and then we don't have an answer there yet. It's just going to say, you know, there are no holes in the file for a compressed file because it won't know. Yeah. Well, a FiMap, it doesn't actually have any compression support yet. We've been trying to get that into the kernel, but for ZFS, we've tried it for, you know, 10 years, but they don't want it. So we got to work something out there.
Hi, Colin. So you have any LU ticket for this? I know this is internal, but any LU we can refer to?
Yeah, we do have a ticket. Unfortunately, I don't have it handy, but come see me after the chat, and I'll track it down. I should have included it in here. That's a great question. 10092. Oh, well, there you go. 10092.
10092. Any other questions? You mentioned that the compression has to be done on 4K boundaries. If it's not, it's skipped.
Yes.
So how does that work? The client tries to compress, and if the compressed value is not a 4K boundary, after the compression, it's skipped, or?
Yeah, I mean, the data itself is just not compressed at that point.
Yeah, but the client CPU just
well,
tries to compress it.
Yeah, it'll try to compress it, and if it can't compress it, if it, you know, if the ultimate result of that is outside of that 4K boundary, then the data is just returned as normal.
Yeah. Can I jump in?
Yeah,
sorry. Yeah. So we start, the minimum compression chunk size is 64K, because that also correlates with the luster layout size, right? And so if it can't compress at least 4K, it won't be compressed, right? Because you're not going to save any space on the server if you can't at least reduce the file size by one disk block on the server. But it will compress it down, you know, in units of 4K, right? So if you get, you know, 2 times compression, it would use 32K of space, right? And if it's 2.01, you know, if it's a few bytes less than 4K or whatever, you're still going to allocate a full block on the server, right? So it's a multiple of 4K.
The comment about 4K alignment is, to me, it's almost maybe misleading. It's sort of revealing an implementation detail. The client doesn't have to do anything, like the user space doesn't have to do anything that's 4K aligned. It's just how we handle internally.
I got that.
Compress at least that much.
Yeah, yeah.
My question more on the line was, that is after we spend the CPU cycles, try to compress, see if it's 4K aligned, then
Well,
give up.
it's not aligned. It's
That's
Redu-
that you shrank it at least.
Yeah, reduced. It's not prediction based. We just actually try to do it, then fail.
yeah,
if it
and
doesn't
there'll
work out.
be
That's
there'll
the
be
logic.
heuristics. So if you know you keep on trying to compress this file and it doesn't compress anything, right? You're writing an MPEG file or whatever, a JPEG, a zip file. It can't compress it. If it can't compress it, then after a certain number of blocks of trying to do that, it's just going to say, you know, don't compress. And
Yeah.
of course, and if you know you have a directory full of MPEGs, just don't turn on compression for that directory, right?
And as we learn more about how this is used and stuff, version 2 will have more smarts built into it.
Have you thought about using offload techniques if they're available in hardware, like QAT or some other hardware?
Yeah,
resources?
absolutely. So that's again, this is one of the reasons why we've kind of opened it up so that we can run multiple compression algorithms here, and we can target specific ones that would leverage hardware a lot better. Because that's as I see it, that's what's coming, right? I mean, I think the Sapphire Rapids processor is going to have gzip decompress support or compress support, and so on. So as the hardware gets better, we're going to try to want to leverage that as much as possible.
Are there enough similarities between compression and encryption to make sense to architect it together, or are they sufficiently different that they should be completely different things?
Yeah, no, I mean, the architecture behind them is reasonably similar.
Actually, I have a comment on that. So the inline kernel, it's using the kernel infrastructure, which is the crypto stuff.
Yeah.
It's the same exact same
crypto
stuff
API,
as
yeah.
the decryption.
Yeah.
And you actually get hardware acceleration with that API since it's being leveraged, if it's available.
Yeah.
Do you see a possibility of offloading those to, say, a DPU on the network interface?
Possibly at some point in the future. I mean, as it stands now, we haven't explored it, but yeah. I mean, ideally in the future, we're going to leverage whatever hardware is available to do this, because, potentially it much more densely packs all the data, meaning your 50 terabyte or 50 petabyte file system just doubled in size potentially. So
If I might speak to that for the usage of hardware. So today we're using the kernel libraries for these, which of course are a priority for any hardware makers to get support into. So if the kernel gets support, we get the support.
Yeah.
And that's our plan, at least for now. We could use something else in the future, but for now we're just going to use the kernel libraries, which generally have excellent and up-to-date support if you're running a new kernel. So.
I thought there might be a lot of questions.
So far, discussion was about hard drives, and do you have considerations for writing to SSD? Because you may save space, but optimal write size internally on the chip of SSD is bigger than 4K. Probably you saved something, but it will be a much more higher latency.
Yeah,
writing to
yeah. I mean, again, this is why our optimal chunk size is 64K. Right, because with lots of QLC flash devices, for instance, that's the erase block size.
And do you consider trim, if you have unallocated blocks, it should be reported to SSD so it can trim that?
Yes.
Okay.
Yeah, I mean, looking to the future, this is a technology I think that will be greatly leveraged for SSD-based systems, and in fact, HDD-based spinning disk systems are somewhat suboptimal for this kind of technology implementation. So, I think as we move forward and spinning Rust goes away, we move to silicon-based storage. This is one of those technologies that will enable us to do that.
That's never going to happen.
So this seems like a perfect application for DPUs, and I was just wondering how much different the code has to be in the framework that you're writing to be able to support the hardware offloads.
Yeah, I mean, we haven't explored that yet. So Colin, that's kind of what I was trying to answer. So we're using the kernel libraries. Oh, sorry. So we're using the kernel libraries. So the answer is nothing. If the kernel has support, which should be a priority for any hardware makers, because the kernel does compression and encryption for a lot of things for the network, for example. So hardware makers tend to make it a priority, get support for the offload there. Offload support's there. We get it. We get it for free. No changes at all.
I was thinking like in terms of like zero copy, so you don't have to even use the CPUs.
Okay, that's something else.
We just haven't gotten there yet. I mean, again, we're baby steps here, right? First introduce a feature that functions and is stable and doesn't blow away a file system. Second, start to pile onto it. And we think we've got a good enough foundation here that will allow us to do this as we progress forward with this.
I'm glad there's a question from that side of the room, because I was worried you all fall asleep over there. Based on the questions, there's great community interest. So
Seems like
get
it,
it into our hands as quickly as possible so we can break it.
Yeah, absolutely, absolutely. And you know, right now I think we're in feature freeze for 2.16. So once we get out of that, then you'll see more stuff come up.
Sure. So let's thank our speaker.
Thank you, folks.